So let's take a look at an example of convergence in distribution. So let's suppose that we start out with a sequence of random variables, xn, that are each normally distributed with mean 0 and variance 1 over n. So in particular, think about what that means. This is an entire sequence where n starts at 1 and is sent off to infinity. So the first random variable will be a standard normal, the second will be a normal 0 1/2, the third a normal 0 1/3, etc. And we want to think about where that converges to in distribution. So what's the distribution as n goes to infinity? Well, it seems like the variance is getting smaller and smaller, and this variance 1 over n will converge to 0 as n goes to infinity. So it seems like a reasonable conjecture to say that actually what we'll end up getting is a kind of a boring distribution, right? It'll be a distribution that's centered at 0, but with 0 variance. So a constant 0. And if we called this boring random variable y, we could ask, what's the CDF of y? This is the thing that we will converge to, right, if we're converging in distribution. Well, that's the probability that y, namely 0, is less than or equal to some little y. Well, I think what we'll have here is that if little y is, let me move this over so I give myself enough room. But if little y is less than 0, then we should have 0, right? Because if little y is less than 0, then it's less than the random variable itself, and the probability that that happens is 0. And then of course, if little y is greater than 0, then that means that the probability should be 1, because you've left all of the probability mass behind, right? The probability mass is entirely focused on the value 0. So, if you want to think about this in terms of a plot, we would say, okay, at 0, well, anytime we are below 0, we will be at 0, right? Below 0 on the y-axis here, the CDF will be equal to 0. And then, since the random variable is 0, we jump up at 0, and then, if we calculate what is the probability that y is equal to 0, that's 1, right? That's the whole distribution. And then, of course, anytime we get above there, so anytime our little y is greater than 0, we are at 1. So that's what our CDF will look like for the target, right? The random variable y is equal to 0. So how do we get there? Well, I think we can notice that if xn is normal 0, 1 over n, then we can always normalize our random variable. And what does that mean? We take our random variable, so any member of the sequence xn, we subtract off the mean, and by subtracting off the mean we have 0 in this case, so we won't have to write anything. And then we can divide by the standard deviation, and that will give us a normal 0, 1. Now, of course, another way to write this is that z is just equal to the square root of n times xn. And so let's think, ultimately we want to know whether fn, right, that's the CDF of xn, converges anywhere. And by definition, this is the probability that xn is less than or equal to little x. Well, that should be the same if we just multiply both sides by the square root of n, then we'll have the probability the square root of n times xn is less than or equal to the square root of n times x. And we did that because now we're asking about the CDF of a standard normal, right? This is our z. So we can write that probability that z is less than or equal to the square root of n times x. And I think we have to think about two different cases, because one case we have x positive, and another case we'll have x negative, and that's going to change. So if x is negative, so x is less than 0, as we send n to infinity, right, this grows really large, and this becomes, this makes it negative. So this value tends to negative infinity. And what's the probability that a standard normal is less than or equal to, in the limit, negative infinity? Well, that'll be 0. And similarly, if x is positive, then this becomes positive infinity. And what's the probability that a standard normal is less than or equal to positive infinity? Well, that's going to be 1 for x positive as n goes to infinity. And notice that what we're getting here is exactly what we called the CDF for the random variable y. That's this thing up here. So we've done it. We've showed that the CDF of xn converges to the CDF of y as n goes to infinity, and that means that we have convergence in distribution.